In this lecture, we will look at certain practical aspects of the design of an electrochemical double layer capacitor. So this is schematic of a capacitor. It looks very similar to that of a battery or a fuel cell. So these are two current collectors, and the major components, that is, of the electrode are porous materials. We have looked at the reasons for the structure when we dealt with how to think through the porous electrodes. So the structure is very similar for a battery or an electrochemical double layer capacitor. So what is important to understand is that the electrolyte, which is filled in between the pores, has a specific voltage window wherein it is stable. For example, if you have an aqueous capacitor, then the voltage window of stability for an aqueous capacitor is quite different from that of a non-aqueous capacitor. So there will be an voltage drop across the capacitor, and this voltage drop should be less than the drop that is required for dissociating the electrolyte. For example, if it's an aqueous capacitor, the voltage drop cannot be more than 1.2. So this is the dominant upper bound for voltage drop in an aqueous capacitor, whereas for an organic electrolyte capacitor, the voltage drop and the voltage window can be larger. It can be 3 volts, and there is a persistent effort to increase the voltage window so that you can store more energy in a capacitor. So often the capacitors are arranged in series because the voltage that can be obtained from a single capacitor is quite less. Therefore, you want to connect them in series to build up the voltage. This introduces certain complications. Because the charge stored in a capacitor that are connected in series is the same, the discharge rate or the current is also the same across these capacitors connected in series. Q is equal to C times V. Therefore, when one of the capacitor has lesser capacitance for some reason, perhaps it's defective, one of the electrode is defective and so on. If that is so, then because of lesser capacitance, you want to keep Q the same. So as Q is C times V, when you have lesser capacitance, there's a greater voltage drop across that particular, let's say, defective capacitor. This kind of differing voltages might be quite deleterious for EDLC, for that particular capacitor, and that particular capacitor would fail. So it is important to avoid such a situation when the capacitors are arranged in series configuration. Typically, you do not also want to be discharging the EDLC completely. So you don't go from 100% charge to 100% discharge. So because the voltage across the line will significantly decrease if that is so. And also the structural changes that occur under complete discharge and is more, therefore limiting the cycle life. So you do not want to have complete discharge of a capacitor. While this might be a lesser problem when it comes to a capacitor, that is, compared to a battery, the structural changes that occur during the discharge of the device is lesser in the case of EDLC. You still do not want to be discharging the capacitor to the full extent. Therefore, you typically operate between 40 to 80% of maximum potential rating. So you do not want to be discharging. That is the main take-home message. So there are other metrics of a capacitor. The maximum specific energy is given by this formula. This formula is, we've already looked at why, the reason behind this expression in a previous um, lecture on how to specify the energy of a capacitor. Because each capacitor comes with 2 electrodes, you have this quantity. Then how to go from here to here is obvious when you consider how to think about the total capacitance of a capacitor. The formula is 1 by C total is equal to 1 by C1 plus 1 by C2, right? Because these capacitors are connected in series. That's the way you add up the capacitance. From that formula, you get this expression. Once you plug in this expression into this, you get this expression. So this is the way to specify the maximum specific energy for a capacitor. Then it's good to go through the notations we had utilized in porous electrodes before coming to looking at this expression. So let's understand the logic behind this expression. So when you have, let's say, EDLC, corresponding to charges here, or charges in, let's say, the electronic conductor, there is a counter charge available. Okay, even though the electronic conductor has a negative or positive charge, corresponding to these charges on the electrolyte side, you have counter ions that are being present. So this is a very important aspect to be understood. Therefore, if you want to have significant or maximize the charge that can be stored in a capacitor, you should also have significant number of ions in a capacitor, in the electrolyte that goes into the capacitor. So if it's because it's a porous electrode, the electrolyte is filled inside the porosity, inside the porous material. So porosity times the volume available for the electrolyte to be stored gives you a measure of the counter ions that are present. So what is C0? C0 is the concentration of the ions in the electrolyte. This is the dissociation constant. V plus times C0 would give you, let's say, the amount of positive charge available in the electrolyte, each number of positive ions available in the electrolyte, and Z plus is the valency times F will give you the total amount of charge. This again is the area per unit volume. So this would give you the amount of ions, counter ions that is available to you, divided by the mass of the solid particles times 1 by epsilon, right? So this specification, please go through the porous electrode. The notations were used for porous electrode to understand this point. So the main take-home message is, if you want to store maximum charge, you should have correspondingly a lot of counter ions present in the electrolyte. So it also has additional effects in when you increase the counter ions that are present in the electrode electrolyte interface. You are depleting the ions that are present in the electrolyte. As you deplete the ions that are present in the electrolyte, your conductivity of the electrolyte is also decreased significantly. So what is important to understand is all these things are correlated. As you charge the capacitor, ions, counter ions are in the region adjacent to the electrode, that is in the electrode electrolyte interface, and while you are doing that, you are depleting the ions from the bulk of the electrolyte. So this would tend to increase the series resistance. So it is important to have sufficient amount of ions present in the electrolyte so as to store a lot more charges in the capacitor. The state of charge is a quantity which we have already seen. In a battery, because the voltage does not change with respect to the discharge of a battery, it is not easy to assess the state of charge of a battery. As opposed to that, it is easy to assess the state of charge of a capacitor. How do you do so? Let's say Vmax is the maximum voltage that a capacitor can give. Let's say this is this quantity. Supposing when the open circuit potential of a capacitor is a particular level, so that is this particular quantity, you can easily correlate the voltage of the capacitor, that is VOCP, to extent of discharge. Supposing you are in this potential, then means that you have discharged the capacitor has about 50% charge left to be discharged. So it is because of this linear change in voltage of a capacitor, it is easy to assess the state of charge of a capacitor. But the disadvantage with the capacitor is that the voltage significantly decreases as you discharge. So you do not want to be discharging the capacitor to 100%. In the next lecture, we will look at a rather intriguing aspect of EDLC, which is not still completely understood. And this topic is about self-discharge and leakage current in a electrochemical double layer capacitor. Thank you.